Hello, my name is Po-Wei from the National University of Singapore. Today, I'm going to present my work on domain-specific augmentations as low-cost teachers for large students, a paper on the shared task at detecting entities in the astrophysics literature. Over the years, scientific document processing, or indeed domain-specific natural language processing tasks, have viewed pre-training transformer models as one of the main default methods of improving performance and accuracies. However, due to a lack of training resources, these models are often restricted in size compared to general language counterparts, leading to lower levels of performance. In this paper, we aim to ask the question, are we able to achieve similar or better results with fine-tuning models larger in size, whilst transferring knowledge from pre-trained domain-specific models to increase robustness? We first describe our task at hand. In scientific literature, astrophysics in particular, we often find that named entities share names or are named after another entity. For example, the word Maxwell in text could refer to the physicist James Clerk Maxwell, a crater on the moon named after the former, a telescope in Hawaii also named after the former, or a set of equations in electromagnetism known as Maxwell's equations. The shared text deal is a sequence labeling task that aims to increase accuracy in named entity recognition in the domain of astrophysics. The dataset accompanying deal is split into four parts. The training dataset and development dataset are labeled and used in training, while the validation and testing dataset are unlabeled and used for inference purposes. The entities are labeled using biotagging, a common standard in NER tests. For evaluation, we have the token level Matthews correlation coefficient and the entity level of macro F1 using seq-eval. We now dive into the methodology, as each sample text in the dataset is quite long and far exceeds the length limit of 512 tokens for most transformer models. We partition the text into sentences by filtering out end-of-sentence punctuations while ignoring a list of abbreviations such as fig, tab, et al. Despite the appearance of long text transformers such as Big Bird and longformers, we use simple partitioning as we reason that the recognition of named entities may not require context of sentences that the entities itself does not reside in. In our work, we utilize domain-specific models such as Cybert as low-cost teachers that transfers domain-specific knowledge to the main backbone model. We accomplish this by using such models to perform data augmentation via mass-LM. Such a method was proved to be an effective method for strong augmentation in semi-supervised learning regimes, particularly in sequence labeling tasks where usual augmentations such as back translation are actually not applicable. We select models with a pre-trained dataset that is similar to the target domain to allow for transfer of domain-specific knowledge to the general model in addition to fine-tuning. For the deal task, we select models such as Cybert, Space Cybert, and Cosmic Roberta as the teacher's model, which also acts as a baseline in our case. Here is a sample text in the training dataset augmented by Cosmic Roberta, a model pre-trained on space-related text. For the backbone model architecture, we want to utilize a sufficiently large model that has more inference power as compared to the base-sized domain-specific model. As large models are usually computationally heavier to fine-tune, we use the adapter architecture, which injects layer of trainable parameters into the transformer layer, training only on these parameters while freezing weights on the original transformer model. This method is shown to achieve comparable results with compared to naive fine-tuning with less computational cost. For the deal task, we select the DBERTA v3 model as the backbone model, which also acts as our baseline. We utilize the augmented text in the form of an additional consistency loss term that we use to train the backbone model. In particular, we add the divergence of the predictions of the backbone model on the augmented text with predictions on the original text. If the model is robust enough, the predictions should be fairly similar. The final loss term consists of the sum of the original cross-entropy loss against the label as well as the additional consistency loss. Our results show that our method outperforms baseline models such as BERT, Cybert, and AstroBERT, a model pre-trained on astrophysical literature. We found that Cybert and Cosmic Roberta seems to perform better on validation and testing dataset respectively, indicating an importance of both independently constructed vocabulary as well as pre-training the corpus on the corpus similar to the target domain for the domain-specific teacher used in our work. Thank you for listening to this talk, and please check out my paper if you'd like to know more.